Now that we've looked at ionic and metallic bonding, we're going to go to the third type of bonding, which is covalent bonding, where ionic bonding is a transfer of electrons between a metal and a nonmetal. Covalent bonding is the sharing of electrons between two nonmetals. So if we start with two fluorine atoms and we generate some dot structures here, we have 7 valence electrons in fluorine. Each fluorine is trying to gain an electron, but there is no element here that tends to lose electrons. So what these two atoms are going to do in order to get their valence is they're going to share a pair of valence electrons. And so when you look at this particular fluorine here, you have 3 unshared pairs of electrons, 1 shared pair. It gets you a total of 8 valence electrons. And since it's being shared with the other fluorine, that fluorine also has 8 valence electrons. And we refer to this as a single covalent bond, or the sharing of a pair of electrons between two atoms. The formula here is going to be F2, and the name of this thing is just fluorine. Whenever fluorine is by itself, it always comes diatomic. There will always be 2 fluorines involved. The structure here, or the formula F2, we refer to as a molecule. A molecule is the smallest particle of a covalent compound that retains the properties of that compound. So a molecule is the representative particle of a covalent compound. We can also look at hydrogen. Hydrogen has 1 valence electron. Of course, hydrogen in the first period there does not need an octet in order to get a stable electron configuration. It only needs 2 to be like helium. So these 2 hydrogens, when they bump into each other, are going to share that pair of electrons. And once again, each hydrogen, in a sense, has 2 electrons as they share that pair. And just like fluorine, hydrogen is going to form a diatomic. One of the ways we can talk about what happens here is that hydrogen by itself, with only 1 electron in an s sublevel, is not as stable as the sharing of electrons. And then we have 2 electrons, 1 upspin, 1 downspin, and a shared orbital, which is referred to as a molecular orbital. We'll talk about that a little later. But you can think about this in terms of energy, because as we've said before, things gain or lose electrons. They form chemical bonds in order to get to a lower energy state. So out here on the right, we have hydrogens out by themselves, and those have a particular kind of standard energy. As they move closer and closer, they're going to reach a point where they share that pair of electrons, and yet the 2 hydrogen nuclei are far enough away from each other to not repel. For hydrogen, that happens around 74 picometers. That would be the bond length of that hydrogen bond. But as they get closer and closer together, that stability is no longer guaranteed, because you're going to have 2 hydrogen nuclei positively charged, and eventually you're going to start to get repulsion that will override the drop in energy from the electron arrangement. Okay, this is a Venn diagram. Venn diagrams are funny. Okay, so we can also look at oxygen. So oxygen has 6 valence electrons. So you got 6 valence electrons around the oxygens. Each oxygen needs to gain 2 electrons. Again, there are no atoms that are interested in losing electrons here. So these oxygens are actually going to share 2 pair of electrons. And the pattern that maybe I hope you're starting to recognize is that when you have nonmetals, in the places where they have unpaired electrons is where they're likely to form covalent bonds. So they're going to share 2 pair of electrons, and that is going to get us a double covalent bond. So double covalent bond is sharing of 2 pairs of electrons between atoms. This is O2, right? And that is oxygen. When oxygen's by itself, it always comes as an O2. Now, you don't have to have 2 oxygens if it's in a compound with a different nonmetal. But anywhere where you have oxygen by yourself, it's O2. And of course, you know this if you watch any medical dramas, right? Somebody comes in, they're having trouble breathing, they said, put them on a O2. That's because oxygen, when it's by itself, is always O2. We take one more step back on the periodic table. We're in that kind of second period in the P blocks, and we've got nitrogen, which has 5 valence electrons. And so if we're tracking that pattern, we see there are 3 unpaired electrons. And so those are the places where they're likely to form chemical bonds. And sure enough, you do that, If the 3 bonds count towards both nitrogens, then each nitrogen, in a sense, has 8 valence electrons, and this is a triple covalent bond, or the sharing of 3 pairs of electrons between 2 atoms, in this case nitrogen. When nitrogen's by itself, it always comes as N2. Now, the examples we've looked at so far are all a particular element bonding with itself, but of course a covalent bond can be between any pair of nonmetals, or it doesn't have to be pair, it could be more than 2 nonmetals, and we'll kind of look at that as we go into talking about different covalent bonds, but this kind of gets us started. And what it shows us is that there's a series of covalent bond or nonmetals which form covalent bonds, and when they're by themselves, they're always going to come diatomic, and we refer to these as the diatomic elements. They're elements which are by themselves always come as covalently bonded pair. They are affectionately referred to as the Magnificent Seven because there are 7 of them. They start with hydrogen, and then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. The reason we refer to them as the Magnificent Seven is that if you start with nitrogen, which happens to be atomic number 7 on the periodic table, they make the shape of a 7, and there are 7 of them. The only one that's kind of out of pattern here is hydrogen, but of course, hydrogen can often be seen as belonging on both sides of the periodic table. It has 1 valence electron, so it belongs on the left, but also tends to gain an electron like fluorine, chlorine, bromine, and iodine, so it could also equally make sense to put it above the halogens there, and so that gives us a more 7-looking shape if we do that.